In today's lesson, we are going to be talking about rates of change. Now, you may remember this phrase, rates of change, when you were talking about equations of lines and you looked at slope. Slope is an excellent example of rate of change, but we don't want to limit ourselves to only talking about rate of change when we have what we call a constant rate of change. So the slope of a line is what we would consider a constant rate of change. It changes at the same rate no matter where you are on that line. But we want to go further and talk about any type of function, not just lines. And we want to be able to talk about rates of change. Now, obviously, because those rates of change are not going to be constant like it is with a line, we are going to talk about what's called average rate of change. So say you have some function f, and you want to find the average rate of change. Well, the average rate of change of f of x with respect to x, well, it depends on where you are on the graph. So let's say you're going from point A to point B for your value of x. Then, to find the average rate of change, you would have to find the y values at A and B and find the difference between those y values and put it over the difference between A and B. So change in f of x over change in x, which in this case is f of b minus f of a, those are the two y values at a and at b, and put it over b minus a, those are your x values. And so this is actually the same as finding the rate of change when you were looking at slope. It was the change in y over the change in x, but because now we're talking about it more generally and trying to apply it to any type of function, not just a line, and we're trying to find the average, we are simply finding the change in y over the change in x, but we have to do it over a certain interval from a to b, and then we can find the change in y for that section over the change in x in that section. Take a look at example 1. We have a balloon being filled with water. Its approximate volume in gallons is v of x equals x cubed over 55, where x is the radius of the balloon in inches. Now clearly here you can tell that the equation is not the equation of a line. Instead, it's a cubic function. Now we want to find out what the average rate of change of the volume is as the radius increases from 5 to 10. So what we need to do is we need to figure out what is the volume when the radius is 5, what is the volume when the radius is 10, subtract those two values, and put it over 10 minus 5. So the change in v of x over the change in x, so v of 10 minus v of 5 over 10 minus 5. v of 10 is equal to 10 cubed over 55, which is equal to about 18.18. Do the same thing with v of 5, so 5 cubed over 55 is equal to about 2.27. On the bottom, 10 minus 5 is equal to 5, and that comes out to be about 3.18 gallons per inch. What does that mean? That means on average, as the balloon is increasing from 5 to 10 for its radius, the number of gallons that it's changing at, that rate that it's changing at, is on average about 3 gallons per inch. Now obviously this number is different depending on whether you're going from 5 to 6 or 6 to 7 or 9 to 10. So this is really just the average rate. So at some points it's going to be actually faster than that, more gallons per inch, and at some points it's going to be slower than that, fewer gallons per inch. But on average, it's going to be changing at a rate of 3.18 gallons per inch. Let's look at what happens as the radius changes from 7 to 15. So we do the same thing, but now we're working with A being 7 and B being 15. So this is v of 15 minus v of 7 over 15 minus 7. So v of 15 is about 61.36, v of 7 is about 6.24, and then 15 minus 7 will end up being 8. Divide those, we end up getting that this is approximately 6.89 gallons per inch. So it seems that when you're working with a larger radius, the rate of change is going to be higher, right? So before, from 5 to 10, we found that on average, the rate of change is 3.18 gallons per inch. But now, when we're going from 7 to 15, we have an average rate of change of 6.89 gallons per inch. Let's take a look at another example. So a small manufacturing company makes specialty office desks. The cost in thousands of dollars of producing X desks is given by this function. C of X equals 0.0009x cubed minus 0.06x squared plus 1.6x plus 5. Find the average rate of change of the cost from 0 to 10 desks. So we are going to find change in C of X over the change in X. So that's the change in cost over the change in production, number of desks being produced. So just before we get into calculating this, let's just talk about what this actually means. This means how big is the difference from going from not producing any desks at all to producing 10 desks? Is that rate of change high or low? Would you expect it to be higher or lower than the next part from 10 to 30 desks? Well, we would probably expect the rate of change from 0 to 10 to be much higher. Why is that? Well, if you're not producing any desks versus once you start producing some desks, then the change in cost is going to be much higher. If you're already producing 10 desks and then now you want to produce 20 desks, that change won't be as high. So let's go ahead and calculate this. So we have C of 10 minus C of 0 all over 10 minus 0. So C of 10 is equal to 15.9, C of 0 is equal to 5. Put that over 10. And this comes out to be about 1.09. Now remember, this is in thousands of dollars. So this is really like 1,090 approximately dollars per desk. That is the rate of change of the cost over the number of desks produced. Now, let's find out what the average rate of change is going from 10 to 30 desks. Now, we said we predict that this should be a lower rate of change because we're already producing desks, as opposed to in part A, when we went from not producing any desks to 10 desks. We had to put in a lot of money for manufacturing costs that weren't there before. Manufacturing costs meaning costs that aren't related to materials that were used to create those desks. All right, so let's do the same thing. So C over 30 minus C of 10 all over 30 minus 10. So C of 30 comes out to be about 23.3. C of 10 we already found in the last problem is 15.9. And we put that all over 20. And that comes out to be about 0.37. Remember, this is in $1,000 per desk. So that means about $370 per desk. That's the average rate of change in terms of the cost per desk over the number of desks produced. So yes, this is much lower than when we went from not producing any desks to producing 10 desks. The average rate of change is much lower when you go from 10 desks to 30 desks because when you're producing 10 desks, you already have certain manufacturing costs that are already calculated in there. With 30 desks, obviously, we need more materials, but perhaps we don't have as much in manufacturing costs that we need to add on.